Hi students, welcome back to your physics class. In your previous class that we have discussed regarding collision process in case of inelastic collisions in the laboratory frame of reference as well as in center of mass frame of reference. Okay, today we will discuss another important concept in your conservation law is conservation of linear momentum in case of a variable mass. What it is? Conservation of linear momentum in case of variable mass. In previous concept, there the mass remains constant during an what motion. But in this case, the mass of an object gets changes. So that is whose mass is variable or in which the mass enters or leaves the what system during its what is a motion. So how that your linear momentum gets conserved in case of your what a variable mass. Okay. So the example for your variable mass, where that the mass gets changes during its what a motion. So that's a simple example for that is it is a rocket. Okay. So what do you mean by a rocket? This is a device. Or you can call it a satellite, or you can call it a what? Vehicle or a what instrument. So what purpose this one is using? It is used to place an what? A satellite. And rocket is a what? Device used to place the what is satellites into the and what object is called as a rocket. Or you can say the another one word is what? The vehicle which is used to place a satellite into an orbital motion is called as a rocket. Okay. So this rocket already you have seen rocket and I will learn a little bit regarding rocket principles in your previous class. So it is based on which principle? So it is based on the principle of what? Conservation of the linear momentum under and what? A variable mass. But mass gets what is changes to the what is motion. Okay. So what is the principle of that your rocket or your propulsion of that what rocket is? Or what is the principle of that rocket? Okay. So a rocket in its simplest form is a chamber. What is a rocket in its simplest form is a chamber enclosing a gas under a pressure, a small opening at one end of the chamber, allowing the gas to escape and is doing so provides a thrust, means upward thrust that due to that the rocket propels in the opposite direction. Okay? So this is a simple principle that is used in case of the what? A rocket principle. What is a rocket? In its simplest form is a chamber enclosing a what? A gas under a pressure. A small opening at one end of the chamber allowing the gas to escape. So you want to what? Eject what your gas is what ejected out at one end of the what chamber to escape from that chamber. And due to that, when you are doing this one, yeah, that rocket, or you can call it, that provides thrust to the what rocket. Due to that, it propels that rocket in the what opposite direction. So this is the simple principle of our what rocket. When that your what gas is escapes from the chamber at one end of the what chamber, which is provided at the bottom of the rocket. Due to that, that provides that the escaping of your gas provides what thrust. Thrust that propels the rocket in opposite direction. Okay, so this is the simplest principle of your what rocket. Okay, so next, already I have mentioned that it is based on the your what principle of conservation of the what linear momentum. So now here, let us derive the expression for velocity of a single stage rocket. So what is the velocity of that your rocket that you want to what derive in this class? Okay. So as I mentioned that this is a diagram for what a rocket. So here, due to the burning of your gas, that gas gets what ejected in these directions. When the gas escapes out at this one end, that provides what thrust to that your rocket. So due to this, that rocket propels in the opposite directions. Okay. So this is the simple principle used in our what rocket. So let us derive the expression for velocity of a single stage rocket. Okay, neglecting its what it is weight. So let us consider what capital M. Capital M is the what total mass. So you want to mention that what is capital M. Capital M be the mass of the rocket, including even what mass of the fuel. Okay, and you want to mention what capital M is the mass of the rocket, and you can say that capital V is the velocity of the rocket at any instant of t with respect to your what ground in the laboratory frame. So here already I have mentioned that the laboratory frame is the one in which where the position and velocity of the given object are measured with respect to and what laboratory to those frames we are calling the what laboratory of frame. Okay, so here so you are measuring the velocities of the rocket with respect to ground. The ground itself some particular uh, place, so is nothing but a what laboratory frame of reference. Okay, so I can call it what inertial frame of the fixed area, fixed position. Okay, next, so let assume that uh, that the gas which is escaping out, the hot gas is ejected out at the bottom of the what rocket. That the vapor gets ejected backward with the what velocities with respect to what. So you can say that the whatever the hot gas is ejected at the bottom of your rocket with a velocity, you can say that small v in the what backward direction, respectively what rocket is. Okay. Next, then according to the law of what addition of velocities, what is the velocity of this gas in the laboratory frame? So you are measuring these things with respect to and what some area, the laboratory frame, where you are going to measure all these things. Okay, the fixed frame. Okay, according to the law of addition of velocity, then velocity of the gas in a laboratory frame will be given by minus v, that small v plus the opposite what capital V, where small v is the what the velocity of the hot gas which is ejected in downward direction, whereas capital V is the what velocity of the rocket in a forward direction. Okay, so therefore the velocity of the gas, uh, the velocity of the what gas is given by capital V minus of small v. You can write it like this also. Okay, so next, same line. It is in the what same line as that of the what velocity of the rocket, which is moving in what a forward direction. So those two are acts in what same straight lines. Okay. Next, let's write the rate of change of your what linear momentum. What is the rate of change of linear momentum of the rocket is given by it is again before that you have to write one more equation. Here it is there. Okay, it is there. So I have written that the velocity of the your gas in the laboratory frame is given by minus v plus of v, or you can call it what capital V minus of v small v. Okay. Then the what is the rate of change of mass of the rocket due to what escape of that gas? What is the change in the mass of the rocket due to what escape of the your hot gases at the bottom of our rocket? The result designated by symbol of what is alpha is equals to minus dm by t. Here, the negative sign indicates what it is that the as the time passes, the mass of the rocket, what it is, gets decreases because of what? The fuel, due to burning of your fuel, the amount of fuel existing in the rocket goes on. What is what decreases so that the mass becomes what decreases. Okay. Then, according to the Newton's second law of motion, the force acting on the rocket, the force acting on the rocket is given by what's dm by dt. So it is what into bracket capital V minus of what is small v. This is the what the amount of force acting on that is what okay. Now you have to write that the rate of change of linear momentum of that rocket. So here the mass during its motion, the mass as well as what the velocities both are what changes. So that's why you want to write the d by dt into what m into v. So you want to according to your Newton's third law of motion, you write this rate of change of momentum of the rocket is equal to what the force acting on that your rocket. So both those two are force. That's why. So these two, according to Newton's third law of motion, so is given by d by dt into what capital M into v. That's is equals to dm into bracket what capital V minus of small v divided by what is 53. Okay, this one. So here the rate of change of linear momentum of the rocket. So that mass is what a variable. It goes on changes. That's why you are differentiate this quantity with respect to what by using a formula of what u into v method. So on doing this, so and simplify these two equations. So you will get dv by dt. On doing this one, so you're getting what capital M into dv by dt plus of what capital V into dm by dt. That's is equals to what? So capital V into dm by dt minus of small v into is what dm by dt. So here what it is we were getting some values. Which one is get cancelled here? So v into dm by dt on the left hand side and what right hand side get cancelled. That's why you are getting in what capital M into dv by dt. That's equals to minus of small v into dm by dt. And then you want to make it cross multiplication. That's why you are getting what is minus of v divided by what capital M into dm by dt. Okay. So dv by dt is nothing but what it is acceptance. So which gives the what the acceleration of your particle at and what any instant of r. This is an expression which gives them what instantaneous value of accelerations of or what a rocket is. Okay. So once you obtain that acceleration of the rocket, then you can obtain what velocity of that rocket is very easy. So here it is what noted that velocity v means the small v, velocity v of the exact exhaust gas with respect to the rocket. The small v, whatever the small v is there, it is the velocity v of the exhaust gas is with respect to the rocket, but not with respect to what your laboratory frame or ground. Whatever the small v is there, the velocity of our exhaust gas, that is with respect to a rocket itself, but not with what it is with respect to the laboratory frame of reference. Okay. So next, now you have to integrate that above quantity. So we'll get on integrating that we are getting what capital V is equal to minus of small v into log of what is capital N plus of C. On integrating that, so dv by dt integration of dv by dt to dt that is equals to minus of integration of small v divided by capital M into dm by dt into dt is there. The dt dt get cancels. Integration of dv you are getting v and v by m here. You take v outside and integration of 1 by m into dm is what integration of 1 by x is what log x log of m plus is what c, where c is the integration a constant. Okay, where c is the what is integration a constant. Okay, next let us assume that v naught be the initial velocity of the rocket before launching it is. Okay, next this one is what at the time of what t equals to still that your rocket is not launched from the launching pad. Okay, and m naught is what total initial mass. Then your equation number 4 becomes v naught is equals to minus of small v into log of what is m naught plus what is c. So therefore c is equals to a v naught plus of small v into log of m naught. So this value, so you want to insert in equation number what of 4. So you will get capital V is equals to minus of small v log of what is capital M plus of is what v naught plus small v log it is what is m naught. Okay. Then after simplifying that, so you are getting what capital V is equals to v naught plus of what small v log of what is m naught by what. So this equation so will give you what the velocity of the your what rocket at any instant of time when the total mass of the rocket is in terms of what is yeah. So this is a small derivations regarding what expression for the velocity of the rocket single stage rocket neglecting its what the rate of the rocket. Okay. Next, so we'll discuss the rocket consisting of an what is a number of what is engines. They contains what the number of engines. The bracket may contains and what double stage or it may three. Say any number of what rocket, any number of what engines can be what constructed inside of what rocket. So what's the purpose of increasing the what your engines stages inside your what rocket? Okay. So here the purpose of adding an engine inside your what is a rocket is to what increase the velocity of the rocket. So here to obtain the high velocity of the rocket, so it is necessary that what you want to do is in order to have a higher value of your what velocity of the rocket, the value of the your exhaust velocity small v must be what is large. That means whatever that hot gas is escaping out at the bottom of a rocket, should be what is large in order to have a high velocity of the rocket. And one more thing, its final mass should be what? It must be what? Smaller than its what? Initial mass. But we have not. Whatever that we have not is what? The initial mass of the your rocket. So in order to have a high velocity, the final mass of your rocket should be what? Smaller than that is what its initial mass. Okay, this is the things that you want to what consider while constructing and what rockets. Okay, so here, what is the necessity of our multi-stage rocket? As already I have mentioned that. So in order to have a higher velocity, in order to increase the velocity of the rocket, so we need and what number of stages in the rocket. The double stage rocket and one next is triple stage. So that is how many number of engines that you require, the fuel engines that you require, you can use. Okay. So here the rockets are what combined together in a series. The rockets are what combined together in a series. Uh, Two or three or more. So you can go on construct. You can combine the number of rockets in one series. To those we are calling it what multi-stage rockets. Here, so in order to escape your rocket from the escape velocity, that velocity of rocket should be what greater than how much of value is 11.2 kilometers per second. In order to escape the Earth gravitational field, the velocity of the rocket is what greater than that of the what 11.2 kilometers per second. Okay, so that should be what very important. The velocity should be what 11 point greater than that of what 11.2 kilometers per second. Okay. Hence, the larger velocities cannot be obtained with the help of a single stage rocket. In order to obtain, in order to have more velocities, we need to more velocities. We need to have what? Any two or more, three stages of a rocket. Okay, so there is a necessity of combining a number of rockets in a series. Okay, so here the first stage is how in the first unit, suppose if you take a double stage. So if, the first stage is a large and heavy. Second stage is small and light comparatively as compared to the previous one. When the rocket is launched into the space, what is happening? The first stage is used first and its fuel is burned automatically. It is what it is. The first stage is used first and its fuel is what burned automatically. It is gets detached. When get is detached, when it is detached at the moment at the second the second stage at the moment the second stage rocket starts what walking with the initial velocity given by the what first stage rocket given by the first stage rocket is now the final velocity will be merely the velocity achieved. What is the final velocity will be merely twice the final velocity, whatever the second stage rocket is achieved. That is how much it is. This is twice the velocity achieved by the single stage rocket. This is the importance of adding a more number of what is uh, engine or stages of multi stages of rocket. This is the main purpose of adding what rocket in any number. So you have to have higher velocities. Okay, so this is about what the necessity of multi-stage rockets. Next, let's discuss something regarding what the basics of angular momentum and the torque. So you know that the momentum is what This is the linear momentum, not angular momentum that we have discussed in the first class itself. The momentum is nothing but which is the total quantity or the amount of motion possessed by the body, and it is measured by the what? Measured as the what? The mass of the body and its what? The velocity of that object. So therefore, the linear momentum P is equals to what? M into V. But what about our angular momentum? So angular momentum of a particle about a what? Fixed point is the what? The moment of linear moment. Is what? The moment of linear momentum is nothing but an angular momentum. The moment of a linear momentum about a fixed point is called angular momentum. So that's the definition of the what? Angular momentum. The moment of linear momentum about a what? A fixed point is nothing but what? Angular momentum. Okay. So let us see how that you are getting a angular momentum. Already I mentioned that angular momentum before that linear momentum is equals to A is equals to M into V. So suppose consider and in order to illustrate, in order to explain the angular momentum, consider a particle of mass M rotating about a what? A fixed point. You can call that fixed point, you can call it what? O, rotating about a fixed point O. Let R be the radius vector and V be the linear velocity of the particle. Then we know that the linear momentum of that particle is given by P is equal to M into V. But here, the angular momentum is what? The moment of the linear momentum of the particle about the fixed point. The moment of the linear momentum of the particle about the fixed point is known as an what? Angular momentum of the particle. It is given by the, how you are measuring this one? It is given by the product of the radius vector of the, it is given by what? The vector product of the radius vector and what? The linear momentum. Simple one. It is the momentum, the linear momentum of the particle about the fixed point. So how you are measuring this one? It is given by the product of the radius vector and the what? The linear momentum of that particle. So that's designated by the symbol of what? Capital L is equals to small r into P. So where r is the radius vector and P is what? The linear momentum. So then it becomes what? Small m into your what? Momentum is nothing but m into v. So I have taken this one. I have done what? R into v. But R into v is nothing but what is you are having omega s. Okay. Here I have done what? M v is R is equals to m into r omega s. But in this case, v is equals to r into omega is the what? The relation between your velocity and angular velocity. Linear velocity and what? Angular velocity. V is equals to r into omega is there. That's fine. So here I have done what? M into bracket r omega into what is r. That's what m r squared is equals to m r squared into omega. But m r squared is nothing but what? The moment of inertia of that body. Okay. That is equals to what? You are having time omega. Okay. This is the angular momentum. L is equals to I into omega. Okay. Next, suppose if you want to write that angular momentum of system of particles, then so what you want to write is let us write the your water. Is your system consisting of what? N number of particles having an angular momentum of J1, J2, J3, and so on up to what? Zn. Then you want to write the total angular momentum of all the particles is given by this thing. And if you want to write it in a simple way, you can write summation of this is what n is equals to this n is equals to 1 to n. So here better to use that k is equals to 1 to n what? N you write rn rk into 2k. Then only it becomes okay. Otherwise it becomes not right. Okay. So this is the total, which gives the what? The total angular momentum of the what? System of particles. Next, you are having another important term that torque gives. Another important term. So you are having what is a torque. So what do you mean by a torque gives? So what's the meaning of a torque gives? The time rate of change of angular momentum of a particle about a given point is known as what I have said. It is the time rate of change of angular momentum. The time rate of change of angular momentum of a particle about a fixed point is known as torque. So see here. So how to get how I have defined that the time rate of change of angular momentum of the particle about a fixed point. So for that, consider a particle of mass m rotating about a what fixed point. Let r be the position vector and v be the linear velocity of the particle. Then the angular momentum. So we know that j is equals to what? R into p. It depends on this one. So simple one. We are getting dj by dt is equals to d by dt into the r into n px. Differences again by using u into v method. So in dr by dt into p plus of r into what? dt by d what? dt. Okay. But here dr by dt is nothing but v into m into v plus of what? R into dt by dt. That's equals what? 0 plus of r into dt by we're having what? dt. But here, so v into v is nothing but what? According to your vector notations, this becomes what? 0. So therefore, you are getting what? Uh, dz by dt. So for that, I have used in a word. What is tau? So the time rate of change of angular momentum of a particle about the what? A fixed point, about a given point is known as what? That's fine. So the tau is the what symbol used for the what torque. That is equals to what? R into is what? E of x. Okay. Okay, this is about your little bit regarding angular momentum and torque. So in these sessions, we have discussed about your conservation of linear momentum in case of variable mass that is in rocket. So for that, we derived a velocity of the rocket. Then we have discussed a little bit regarding multi-stage rocket, angular momentum, and which one is what torque. Okay, thank you.